Okay, so we'll continue with our discussion of chapter 3, inductors and capacitors. I will go over the remaining equations for inductors and then theory about the capacitors. One point about the homework, it's due on Thursday. There are several questions in there. Many of them are conceptual. Some of them are problems. Problems we will cover on Wednesday, but do not wait to get started on the homework. Okay. Based on the previous lecture and today's lecture, you'll be able to answer at least half of the questions. All right. So again, do not wait to get started on the homework. It's due on Thursday. I will cover most of the theory today, and then we'll look at the problems on Wednesday. Okay. So when we look at the inductors and capacitors, they have standard VI equations, the equations that relate the voltage and current for both the components. For inductors, we usually talk in terms of an input current, and so the resulting voltage is given by this equation. V is equal to L di over dt, where L is the value of the inductor, and then rate of change of current di over dt. Okay. When we get to capacitors, you will see that the capacitor equations also have a similar structure. Inductors and capacitors are duals of each other. So they are very similar in many ways, but they're also opposite in many ways. Okay. But the equations, the voltage and current equations for both components are very similar to each other. So here again, the voltage current equation, meaning the voltage as a function of current or dependent on current, is V equals L di over dt. And then the reverse IV equation, meaning if you're given the voltage and you would like to determine the current, you simply integrate both sides. All right, you integrate both sides, meaning the inductor is the integration of the voltage, right? Integration is nothing but summation, right? You slice up your quantity in individual pieces, and then you sum it up over a certain period of time. Okay, in this equation, the limits of the integral are basically specifying the point in time which we begin analysis and the point in time where we end our analysis. So as an example, let's say we are monitoring a system for a period of 24 hours. Okay, 24 hours or 1 hour or whatever. But right there in the middle, we need to analyze maybe between 59 minutes and 60 minutes. So the point in time which we begin our analysis would be 59 minutes, and the point in time that we end our analysis would be 60 minutes. So T0 will have a specific value. That value could be anything. It could be 0, it could be 1, it could be 2, it could be anything. But it simply notes the point in time where we begin analysis. And then the other end, of course, is when we end our analysis. And those values can be anything. So T0 and T would take any values. The limits of the integral are specified as the variable T is because the voltage and current are functions of time. If you remember from last class, energy is being transferred in and out of these components, right? Energy transfer cannot take place instantaneously. It takes a certain amount of time for the energy to be transferred into the inductor and out of the inductor. Okay. So the voltage and current have values that are functions of time. Expanding on that, notation sometimes would have V of t or I of t simply means it's voltage or current as a function of time. Sometimes they are referred to as just V or I. Sometimes they are referred to as functions of time. In most cases, they mean one and the same thing. You might also come across subscript notations. So you might see VL of t or simply VL. You might also see IL of t or simply IL. In this case, it's simply referring to the notation. The subscript notation is simply referring to that component, that specific component. If you have multiple components, meaning multiple inductors in the same circuit, you might be IL1, IL2, or VL3, VL5. That's all it means. Okay, it's simply indicating the component that it's referring to. So VI equation is V equals L di over dt. You flip it and integrate, you get I of t is equal to 1 over L integral of the voltage. I will talk about this later on when we actually go to solve the problems. That just refers to the initial energy that is stored in that inductor. Okay. Mathematically speaking, if I equals 0, or if I is not 0, sorry, if I is a constant value, if it's a constant number, what do we get? Right? Mathematically, we know if I is a constant value, then the derivative would be equal to 0. So voltage would be equal to 0. Now, electrically speaking, if I is constant, it's a DC voltage or a DC current, right? The value of that current is not changing with respect to time. If you plot the value with time on the x-axis and voltage or current on the y-axis, a DC current or voltage will have a fixed value. So it means, conceptually, it means if you apply DC voltage or current to an inductor, at some point in time, the inductor will have maximum stored charge. And when it reaches maximum charge, the bucket is now full, then the inductor behaves like a short circuit. Okay, current will just flow through the inductor unopposed. Okay, again, it's simply a coil of conducting wire. So once the magnetic field has absorbed as much charge as it can, from that point on, it behaves like a short circuit. Mathematically, it's easy to see, right? Mathematically, we see V is equal to L di over dt. If I is constant, di over dt is 0. Hence, the voltage across it is 0. Conceptually speaking, the magnetic field absorbs all the energy it can, stores all the energy that it can, and that from that point on, it behaves like a short circuit. When it's a short circuit, both ends of the inductor are now the exact same node, so voltage across it equal to 0. And so we say that if you apply DC to an inductor, it behaves like a short circuit. But it behaves like a short circuit only after it reaches full charge, only after it reaches maximum charge. Okay, not before that. So it behaves like a short circuit only after it is fully charged. So let's take 10 seconds, longer if you need, and then let me know if you have any questions. Yes. All right. Henry, you mean for the inductor? It's basically, no, that's just an association. So that's a good question. Basically, the question being asked is what is actually Henry? What is the level of one inductance, right? Is that what you're asking? So 1 Henry is the inductance level or the capacity that produces 1 volt for every 1 ampere change in current that's flowing through that inductor. So if 1 amp is being applied to an inductor, 1 amp of current that's applied, and it produces 1 volt across that inductor, then that inductance level is 1 Henry. All right, any other questions? So yes, Question? Mhm. Yeah, because a battery will provide a rated voltage or current that doesn't change, right? A battery is a DC source. So it's a kind of a DC source. And so whether it's a DC voltage, whether it's a battery, whether it's an adapter, coming from the power outlet, the value of that battery or that source is constant with respect to time. So when it's constant, at some point in time, when it reaches full charge, inductor behaves like a short circuit. And then an important follow-up point I want to make refers to chapter 5. When current flows to the inductor, magnetic field is set up. That magnetic field is going to store that energy. And as I just stated, once it reaches full charge, it behaves like a short circuit. But once that magnetic field is set up, it gives rise to an opposing voltage. And that opposing voltage has polarity that is opposite to the initial current that is being applied to that inductor. So that opposing voltage will oppose any change in the input current. I will repeat. When you apply an input current to the inductor, you have a magnetic field. That magnetic field will give rise to an opposing voltage that has polarity that is opposite and opposes any change in the input current. It does not oppose the current itself, but it opposes any change in the value of the input current. So when it comes to AC voltages and currents have constantly changing with respect to time. So when it changes, the inductor magnetic field opposes that change. And we will study this in depth in chapter 5 in AC analysis. Okay, so for DC, it behaves like a short circuit, but for AC, there is opposition. That opposition is not direct, so it's not resistance. It is termed as reactance. And again, this is something we'll study in chapter 5. But I'd like to point this out right now because it refers to the inductor. Okay. One final slide about the inductor is the equations for power and energy. It's rather straightforward. Power is always the product of voltage and current. P equals VI. We simply plug in the value of the voltage in there, right? LdI over dt. So voltage, which is the product of the inductance and the derivative of the current, simply plug into that equation and you get Li di over dt. That's all it is. And again, you don't have to memorize these equations, but you should have the ability to recognize and then apply them to solve your circuits. And then, of course, power is the rate at which work is done. That's energy. And so W is half Li square. Half Li square. Okay. Okay, so from here, let's go into capacitors. And again, capacitors are very similar to inductors in terms of, well, functionality, that it's an energy storage device, and also in terms of the voltage and current equations. So capacitors are nothing but two conducting parallel plates separated by a dielectric layer. Dielectric in this case refers to an insulating material. You could take the two palms of your hands, put them together. They are separated by air. Air is an insulating material. So if you measure the capacitance between your two palms, of course, we don't have any device handy that can measure the capacitance because it is going to be very, very small. But there is capacitance present nonetheless. Okay, especially if it is a conducting material like a cable. A USB cable, for example, has 4 conductors flowing through it. Plus minus 5 volts. So 0 and plus 5 volts. And then 2 cables for data plus and data minus. So there's at least 4 flowing through a standard USB cable. Okay. These 4 cables are conductors. Conductors that are insulated from each other, separated by an insulating material. So there is capacitance all along the length of any cable. Okay, you could take a simple coaxial cable that has two conductors. They are separated by an insulating material. There is capacitance present between those two conducting material. That capacitance does not rise to the level of interference. Okay, if it goes long, maybe let's say 15 feet, 25 feet, or 50 feet, then yes, it does rise to the level of interference. But again, any two conducting materials separated by an insulator, you have a capacitance. So this is a conducting plate, and the other end also a conducting plate separated by an insulating material. The symbol for a capacitor is simply two parallel lines of equal length. This is not equal right now. Sometimes they are concave, like the one shown in the figure here. If there's an arrow through it, it simply means it's variable. That arrow actually applies to resistors and capacitors. Applies to resistors, inductors, and capacitors. Excuse me. Capacitors, like resistors and inductors, are not polarized. They do not have any polarity. Okay, you can connect capacitors either way. It does not have polarity except for an electrolytic capacitor. An electrolytic capacitor is is a special type of capacitor that is comprised of two thin conducting polymers, well, not polymers, two thin films, conducting thin films. One of those films is coated with a gel-like material. The gel material is very, very thin, right? Sometimes they just coated on, like sprayed on. And then you wind both of them out into a spiral cylinder. And that gel-like film acts like an insulating material, but it needs to be activated by a voltage applied in a specific polarity. And hence, these capacitors, again known as electrolytic capacitors, they do have polarity, just because it needs that voltage to be active to activate that gel in a specific manner. For all other capacitors, you can connect them in a circuit without any polarity. So let's see how they would work. I'll explain a little bit of the physics, but after that point, I will tell you to leave the physics on the side. Okay, so let's say you have a capacitor. Capacitor initially does not have any charge, any voltage across it, and you connect it to a voltage source or a battery as shown in this figure. Remember switches from chapter 1? This switch is open. At a certain point in time, you're going to close that switch. When that switch closes, the battery is now connected to that capacitor. There is a charge imbalance across that. So battery is at a higher level, capacitor is at 0. The positive terminal of that voltage source attracts the electrons in the wire and that and the top plate of that capacitor. So the electrons start moving in a counterclockwise direction towards the positive terminal of that voltage source. When an electron moves out of its place, it leaves behind a hole. In semiconductor physics, a hole is said to have a positive charge. We have electrons and we have holes. If you take EE 321, which is the follow-on course after 201, you will learn about semiconductor physics. So again, electrons have negative charge. When an electron moves out of its spot, it leaves behind an empty spot. It literally is known as a hole. It has a positive charge. The effect of an electron moving out is that the space now has a net positive charge. So when an electron moves away from the top plate of the capacitor, it now has one positive charge. At the other end, what happens is you have the negative end of the battery that repels the electrons. And so now electrons are being built up on the bottom plate of the capacitor. So for every positive charge that moves away from the top plate, you now have a negative charge building up on the bottom plate. And so here, again, the electrons are moving in a counterclockwise direction. Current is always stated as flowing the opposite of electrons. And so if electrons are flowing in a counterclockwise direction, we say current is flowing in a clockwise direction, which aligns with passive reference configuration. Current from a source always goes from minus to plus. Current for a passive component always goes from plus to minus. In this case, plus is at the top, minus is at the bottom, and current is flowing in that direction. At some point, the charges build up and the voltage across that capacitor will measure Vs, meaning at some point Vc will equal Vs. At that point, there is no more charge imbalance. Capacitor voltage Vc has reached Vs. Since there's no more charge imbalance, electrons will stop flowing through that circuit. We say the capacitor has reached full charge. Okay, so the moment where Vc equals Vs, we refer to it as full charge. Let's take a pause while you think over all of that. Let me know if you have any questions. There's an important point that I will make about capacitor current, but after we finish this discussion. Yes. So the question being asked is what happens once it reaches full charge? Well, once it reaches full charge, electrons stop flowing through the circuit. Yes. So question being asked is examples of real life applications of capacitors. You all have been using it for many years. Every touchscreen you have ever used is a capacitive touchscreen. If you all remember, or maybe some of you may have used a screen that requires a pen, stylus pen. Those were resistive touchscreens. The resistive touchscreens require a pen because they need, so you do not actually need a pen. If you push down on it, it needs a sharp point where it takes the pressure and changes the resistance. Okay, resistance of the material that's inside there. Capacitive touchscreens work the opposite way. When your finger touches the screen, it actually behaves like a capacitor, and the capacitance that is measured is translated electrically, and that's how the screens would work. That's a very, very simple low-level explanation. Okay, so before the capacitive touchscreens came out, you had resistive touchscreens. The resistive touchscreens, you could actually use them if you applied enough pressure to change the resistance of that screen material. But it was easier to actually just use a stylus pen. So you had the Palm Pilots that came with a stylus pen, and you could actually operate it with the nails of your fingers. Again, the nails of your fingers make a very sharp point. So you can use those. There are still some devices out there, if you can find them like old enough or cheap ones, that use resistive touchscreens. But capacitive touchscreens are now mainstream in all devices. One of the earliest examples was, when Apple first came out with the iPhone, they were going to use a resistive touchscreen. But there was, I can't remember, I think it was out of Stanford or Berkeley. There were a couple of doctoral students who worked on this capacitive touchscreen technology, and they published the paper, and they started, they created a startup. And then Steve Jobs purchased that startup and then integrated that capacitive touchscreens into the iPhone. So they were the first ones. They bought or purchased this technology, and they integrated into the iPhone. Again, that's an example of a capacitor One of the other examples is a camera flash. So not the ones that you have in your smartphones, but do you ever hear a whining noise after you press a camera shutter? That whining noise is a capacitor being charged up. So it stores the energy, and once you press the shutter, all of that energy is released all at once into that light bulb, and that light bulb just flashes, hence the name flash. So that's an example of where you would use a capacitor. Okay, good discussion. Any other questions? So at this point, I will tell you to leave the physics on the side and just think of it in terms of electric circuit analysis. We established that the capacitor is separated by an insulating material. So are electrons passing through that plate or through that insulating material? Someone says yes. How many agree? How many say no? The answer is kind of yes and no, but largely just no. So we would think that the capacitors, electrons are flowing through the circuit, and I stated, right? Electrons are flowing through the circuit, and I said current would flow through the circuit. And this is the important point. This is exactly the reason why I would say leave the physics on the side and think only in terms of electric circuit analysis. So electrons are moving in the top half of the circuit right here and the bottom half, but they do not actually flow through the capacitor itself. Because it is separated by an insulating material, it can never pass through. So my first thought when I first started learning capacitors more than 30 years ago is exactly the same, that electrons are passing through the capacitor, right? Because we always refer to as current flowing through. Current is flowing through the resistor, current is flowing through the inductor, current is flowing through the capacitor. And circuit analysis, yes, we will refer to the current flowing through the capacitor. But when we talk in terms of physics, electrons do not pass through the capacitor. It took me a long time as a student to understand that point. Okay, electrons do not pass through that capacitor. Electrons are moving in that circuit, but they don't pass through the capacitor. Yet the current we refer to as flowing through the capacitor. So leave the physics on the side. Just think in terms of electric circuit analysis, that the capacitor current is passing through the capacitor, similar to an inductor, similar to a resistor. It takes a while to reconcile both together. Okay, so at the beginning, when students start out, I tell them, don't think of it in terms of semiconductor physics, just think in terms of circuit analysis. All right. Any questions? So I'm going to jump ahead a few slides, and I'm going to talk about the differential form of that equation, right? Capacitor voltage is given by C dV over dt. But just conceptually, remember, I just stated, there's a charge imbalance. VC builds up to the level of that voltage source. The point when VC, capacitor voltage, equals Vs, the electrons stop moving in the circuit, meaning the current reaches a value of 0. So when VC equals Vs, electrons stop flowing through the circuit. When they stop flowing through the circuit, current stops flowing through the circuit. So I reaches 0. Capacitor behaves like an open circuit. Make sense to everyone? So inductor behaves like a short circuit. Capacitor behaves like an open circuit. So when you apply DC, capacitor behaves like an open circuit. Only after it reaches full charge. Until it reaches full charge, electrons are flowing through the circuit, so current is flowing through the capacitor. Once it reaches full charge, it behaves like an open circuit. And then the point again, with AC, it's constantly changing. So if it's constantly changing, then electrons are constantly flowing through the circuit. Okay. It's only for DC that it acts like an open circuit. For AC, it's constantly changing, it's constantly moving. So that's a lot to think, a lot to take in. Think over that. Let me know if you have questions. There's one final slide I want to cover. There's not much in that slide. And that slide is almost the last slide right there. Adding up inductors and capacitors, if they're connected in series and parallel, inductors add up the same way as resistors, capacitors the exact opposite of resistors. Meaning if inductors are connected in series, you simply add them up. If they're connected in parallel, it's the reciprocal. Capacitors are the opposite. So capacitors in parallel add up C1 plus C2 plus so on and so forth. And inductors in series add up the same way as resistors. Get started on the homework. Most of the conceptual questions you will be able to answer based on the 2 lectures. And then on Wednesday, I'll go over the problems. And then you'll have about, well, day and a half to get done and finish that homework. Okay, I'll be in my office later this afternoon. So if anyone wants to stop by with any questions, feel free. Yes, question? Okay, all right.